All right, let us continue forth with new forces, new problems, new ideas, still Newton's laws. All right, so the idea here is we're going to introduce ramps. So we're essentially still doing 2D problems, but the two dimensions might be slightly different than just the horizontal and the vertical direction, as is the case with ramps. You may have covered ramps as an example problem in, say, your high school physics class. Really, it is absolutely no different than everything that we've been doing. You just look at what's going on in each dimension. But since you are free to put down a coordinate system, those two dimensions can be whatever you want. Perhaps up and down the ramp and perpendicular to the ramp. And then we will talk about friction as well. So let's see, where did we end last time? We were talking a little bit about tension. Just to recap, the idea, thank God for tension, if you're, say, a tightrope walker, or you're using ropes and pulleys to, for example, hold your legs stationary to mend a broken bone. The tension force is a real force. There is tension that goes throughout the string or cord or whatever it is, and that tension can provide a force. And again, remember that this force originates when you have a rope or a cord attached at two ends or being pulled by two different things on both ends, and they are pulling on the rope with some sort of force that allows for the cord or rope to be taut or stiff. That stiffness creates a tension throughout the rope. So that if we were to look at any individual little molecule of rope, it would be being pulled to the left and to the right with this same tension force. The exceptions of where it is not both pointing to the left and to the right is at the endpoints. So in this case, both of my hands are feeling a tension that is pulling them towards one another as I pull on the rope. Again, a result of them pulling on the rope in the opposite direction. And then, of course, if it is a case where the rope remains slack, there is no tension force. It assumes that the rope essentially is rigid for there to be a tension. And this can be very helpful. For example, in the case of the tightrope walker, what's going on there is when you stand on a tightrope, the rope bends a little bit due to your weight. I'm doing a free body diagram of the person. Their weight is pulling them down, but they are in contact with the rope on both sides of their feet. Those two pieces of rope exert a tension force that points along the rope away from the person or the object that is touching the rope. So even in the case where the angle is some small value like 5 degrees, which might be the case here, that sets up a system where the tension forces are at slight angles. They are not perfectly horizontal. There are slight angles to them, so there's a very, very small vertical component that is associated with each of these tension forces. There's one for the left, there's a slight upwards here, and one on the right, as well. Those two tiny little components in this case are what must be balancing gravity in the case of the tightroper, who is not accelerating towards the ground or accelerating into the air. If these weren't imbalanced, the person would accelerate. Alrighty. So I wanted to talk about ramps first. So let me draw a simple picture of a ramp. It could be the case, maybe this is the setup, that there is a box that is attached to a ramp, or that is attached to a wall by a string, and it rests on a ramp, where the ramp is at some angle relative to the horizontal. Perhaps the cord snaps and the object or the box begins to accelerate downward down the ramp. How fast does it accelerate down the ramp? Is it just accelerating at the rate from gravity, like in the case of if it was just free fall? Or does it accelerate at some different rate from gravity? And of course, if there's other forces like friction and whatnot, then you have to take that into account as well. All right, so if I wanted to say, put some numbers, say you have 5 kilograms of dry ice on a ramp that makes an angle of 30 degrees above the horizontal. The rope breaks and the ice then has what acceleration? Now, it would be perfectly plausible to analyze this using Newton's laws. What you might do first is the usual. I'm going to set up my system. I'm studying the motion of this block of ice. So that is my system. I can look at what is touching the system. And this is after, by the way, the rope has broke. So let's get rid of the rope. What is touching the ice? Well, it's in contact with the surface of the ramp, so I might call that F ramp. Gravity, of course, is acting on the piece of dry ice. And that appears to be it. That's the only things that are touching the block of ice. So my free body diagram might look like this. There's a force pointing downward. That's the force due to gravity. And then it is touching the surface of the ramp, so I would imagine there is a force that is pointing perpendicular to the surface. I'm calling this F ramp. Again, where if I were to draw the surface, which is not a force. Really, I should not be drawing it in this picture. Or I should have used really a different color. I'll use blue. Again, just to remind yourself that these surface forces, are point perpendicular. If we're calling it, say, the normal force. We will see today, friction is essentially another surface force. It is that the surface can exert a force on the object, but rather than it being perpendicular to the surface, it is parallel to the surface. When it's parallel, it's called friction. When it's perpendicular, it is often called the normal force, or of the contact force. All right, so back to the forces at hand, gravity and the surface force. It is clear that there are forces acting in the vertical direction and forces acting in the horizontal direction. If I define up and to the right as positive, then I might write Fg as something like 0, minus mg, because it's pointing downward. And then if I stare long enough at the direction that the contact force is acting in, and let's see, I'm actually going to redraw it because it's going to get busy. If I wanted to do this in the XY direction, and here is the contact force, and then here is the ramp. You can stare at this for a while and convince yourself that this angle and this angle are the same. They are the same angles. And so therefore I might write that the force from the ramp is, whatever the magnitude is, times, in this case, sine in the x direction, and then whatever this is, times cosine in the y direction. Again, and where am I getting that from? I'm getting that from identifying that this is a triangle, particularly a right triangle. where the force of the ramp is the hypotenuse, then there's a vertical component and a horizontal component, where this is theta. And then I could write down Newton's, with these two forces, I could write down Newton's second law for both the x direction, and I would get an acceleration in the x direction horizontal. And I could write this down in the y direction, and I get an equation for what the acceleration is doing in the y direction. But if we're talking about a box going, say, down a ramp, I have some sort of ramp, I have this box, it goes down the ramp. It's not the horizontal and vertical directions that are actually the most interesting. I could ask, how long does it take for the block of ice to get to the base of the ramp if, say, the height starts at 2 meters? What really is the more relevant directions that are worth analyzing is what is the piece of ice doing in the direction along the ramp, up the ramp, down the ramp. And then the second dimension that is perpendicular to that would give you what is going on in the direction that is perpendicular to the ramp. The motion along the ramp is telling you how fast it's speeding up or slowing down or turning around or whatever along the ramp. The perpendicular direction is telling you something about whether or not the box is losing contact with the ramp. Is it flying off the ramp? Is it sinking into the ramp? So let me redraw the ramp. And then I have the box that I'm studying. Let's see, it looks like I highlighted it blue above. So instead of doing the horizontal and the vertical as my coordinate system, I'm going to instead think of a coordinate system where one of the axes lies along the ramp. So this I will call axis 1. And I'm not going to call it x because x usually means horizontal, so I'll just call it axis 1. And then the other coordinate system is going to be perpendicular. I will call that axis 2. And if you take this, if this is confusing to you, you could take this and you can imagine if you just rotate your image a little bit, it is again looks something like an axis where there's a horizontal component and a vertical component. But here I'm just drawing the axis at a slight angle so that one of the axes goes kind of diagonally from the upper left to the lower right, and then the other axis goes from the lower left to the upper right. And rather than calling them axis 1 and 2, because that's going to take too long to write, I'll call it axis alpha and axis beta. And I'll put some arrows to represent which directions I'm going to call the positive directions. And again, you are free to do this. You can put down a coordinate system to be whatever you want. Typically, people pick horizontal and vertical because that's what makes the most sense for the problem. In this case, what might make more sense is what's going on along the ramp, because that's actually what we're interested in, and then what's going on perpendicular to the ramp. Again, the nice thing about choosing an axis that goes along the ramp is since that's what we're actually interested in and what is going on along the ramp, I'm essentially turning this into kind of a 1D problem. As long as I can figure out what's going on in the alpha direction, I'm done. And this is theta. So just like what we did before, where if you had some force, and let me recopy this, because that's going to get a little sloppy. I'll even make it a little bigger. So now let's look at, I might try to get rid of some of the ramp just so that there's not quite so much going on here. So I'll leave it as a dotted line so you can still see kind of where the ramp is. Now, the nice thing here is I could go back to my free body diagram and translate the forces onto this new image. The normal force is really swell because it points perpendicular from the surface. But the way we've drawn this now, the force from the ramp points entirely along this, what I'm calling the beta direction, the direction off and into the ramp. So that's nice, because then if I write F ramp in this coordinate system, I might write this as 0, n. Where again, this is no longer x and y, this is what's going on in the alpha direction, and this is what's going on in the beta direction. That black arrow, F ramp, only points in the beta direction, which again, if you tilt your head and rotate your head, you can convince yourself it's the vertical direction, but it's at an angle relative to the ramp. Now the trickier one is gravity, which points straight down still. So here's F gravity. But notice now it does not point along the vertical direction, so I cannot write it as 0, minus g, because it points a little bit in the alpha direction and a little bit in the beta direction. I can draw dots to represent that. There is a component here which is F gravity in the alpha direction, and then there is a component here which is F gravity in the beta direction. And so now the task is to figure out what are those two components. Let me erase, just because this is busy enough. Now, if we knew the angle, if we knew an angle and could draw a right triangle, we'd be done, because then we could just do SOHCAHTOA. And we actually can do that. My claim, actually I shouldn't have erased this. My claim is that there is a triangle right here. I'm trying to find a highlighter that will work. That this is a right triangle, that I've drawn it there in green. And this angle right here is also theta. Now we need to prove that. We know theta is the angle of the ramp, and now I'm claiming that this angle right here, which is not really related to the base of the ramp in any way, is also theta. Let me show that here. I'll start by drawing gravity again. I'll over-exaggerate and point it straight down, so I have something that's a little bit easier to work with. I'm going to get rid of the axes that are not super relevant for us for this problem. So really this is just an exercise in geometry of just finding all the triangles. There is one triangle right here that I'll trace out in green. There is a right triangle. Why is it a right triangle? Well, you can identify here that this is a right angle. And one of the sides has angle theta. So this is so redrawing it over here. The triangle I just drew in green is this. Now there's some other angle, I'll call it phi. But we know what phi is. Phi plus theta must equal 90 degrees. That is the property of triangles. The three angles must add up to 180. Since one of them is 90, the other two better add up to 90. So then this equals 90 minus theta. So you know actually what this angle right here is. That is phi. Okay. That's not the angle I was talking about above, though. But the connection is to then, I think I just have to make another copy of this. As I tried to do this meticulously without it being too confusing. So again, let me redraw gravity pointing downward. I get rid of the parts that I don't care about right now. I might even get rid of the parts of the ramp that I don't care about to make it even more obvious. We just determined that this is phi. But if you look just at the red lines, you should hopefully appreciate that this is a right triangle, a right angle. Kind of exaggerated, but if you kind of zoom in, at the ramp, where the ramp and that red line hit, that is a right angle. But then there's also phi, which we just determined, and there's this angle here, which I'll just call question mark, that make up that right angle. So we also know that phi plus whatever that question mark is must therefore equal 90 degrees. Therefore, the question mark is 90 degrees minus phi. But phi itself, we just said, was 90 degrees minus theta. The 90s cancel, the minuses cancel. This gen is just theta. So indeed, if I, let me move this up. If I paste it yet again, what did we just show? We just showed that if I were to draw a vertical line straight down, that this angle here is also theta. Now that is useful because just like when we had sine and cosine to break something into the horizontal component and the vertical component, we can use this theta to break the gravity vector into the part that is along alpha and the part that is along beta. How much is gravity pulling the box into the ramp versus how much is it pulling it down the ramp? Okay, now this is theta. So now the triangle of interest is something that looks like this, where this is theta. This side is now the magnitude of the force due to gravity. And there is now a component, which I'll draw in red, this component here, which is the part along beta. And there's this part right here, which is the part along alpha, or up and down the ramp. So then, again, by SOHCAHTOA rules, I can look at which is the opposite side, which is the adjacent side. The force due to gravity, or rather, I won't write it as a vector, along alpha, or along the ramp, is the magnitude times sine of theta. Because I'm looking at along alpha as the opposite side. The opposite side is the sine. Then I have the component of gravity along beta, that is the adjacent side. So then I would write this as FG cosine theta. Maybe a minus sign in front of either of these, depending on which direction I define as positive, which direction I define as negative. For example, going back to what I wrote above, I can now write FG is the component that is along the ramp. So we said along the ramp is the magnitude, so that's just mg sine theta. And then the component that is into the ramp, into and out of the ramp, or along beta, that was mg cosine theta. But since into the ramp is the negative direction, there's a negative sign here. Because I define the positive direction as the direction going off the ramp, not into the ramp. And then I'll recopy the surface. What did we say? We said this was 0, comma, positive n for the surface of the ramp. So again, what you're doing is you're just changing coordinate systems. You're just saying, instead of looking at it horizontally, vertically, I'm going to look at it as a long ramp and perpendicular to ramp. So then what can you do? Again, Newton's laws still apply. There's nothing built into these about it being in the horizontal or vertical direction. So I can still write down the vector force of the surface plus the vector force of gravity equals the mass of the box times the acceleration of the box. But now I can break it into either, instead before we did the x direction in the y direction. Now I will do a long ramp, or what I called alpha, and perpendicular to ramp, which I called beta. So along the ramp, that is, if I get my highlighter back out, that was these components. So there I would say, if I allow for the signs to matter, it was mg sine theta plus 0 equals mass of the box times the acceleration of the ramp of the box along the ramp. Or that g sine theta equals the acceleration along the ramp, which is greater than 0. What does that mean? That means that the box slides and accelerates in the positive alpha direction, which in this case, if we go back up to the top, since we drew the arrow in this direction, positive is down the ramp. Since this is positive, that means that the ice slides down the ramp. And this gives us exactly what that acceleration is. We don't have to worry about angles or anything anymore. This is exactly how fast it's accelerating down the ramp. If I were to tell, I could think of this now as a 1D problem. If I just looked along the ramp, this is a 1D problem along the ramp with this acceleration. In the perpendicular direction, I then have n minus mg sine, cosine theta equals the mass of the box times the acceleration in the beta direction. Which again, we can think about this and say, okay, if the ice is sliding down the ramp, or the box, or whatever it is, I think it was ice, assuming that the ice block is not leaping into the air or literally sinking into the ramp, this must be 0. If it were not 0, that means there would be some sort of acceleration perpendicular to the ramp. For example, if it was positive, that would mean that the ice block would start to lift off the ramp. If it was negative, that would mean it would start to sink into the ramp. So then you can see that this then shows that the contact force is mg cosine theta in this case. If you want to call it a normal force, again, hopefully this demonstrates the normal force, or what the bathroom scale would read if there was a scale underneath the block of ice, does not read your weight, mg, but it reads something less, mg cosine theta. And again, I always like to interpret these to make sure I have some intuition about what's going on. This contact force is normal force. Suppose the ramp were to shrink so that there was no overall angle. It was just a zero angle. Theta is 0. If I look at this expression, theta of 0 means that n does become just m times g. Cosine of 0 is 1. In that case, the contact force is exactly your weight. And that should make sense. It's just like you standing still on a bathroom scale. But then as I increase theta so that there's more and more of an incline, there's still a contact between the surface. The surface is still working on the object. It's pointing out perpendicular to the surface. But notice that as theta gets bigger, cosine gets smaller. It goes from 1 to 0 as you go from theta of 0 to 90 degrees. And again, that should make sense that when you get to the most extreme case of 90 degrees, this contact force goes to 0, and that should make sense. There's no reason, there's nothing keeping the object attached to the now vertical ramp in this case, and it will just fall off. It's always nice when you have expressions like this to make sure they make sense intuitively. So let me do one more problem with ramps. What space do I have? I have plenty of space. Suppose you are moving apartments and you are pushing material into a moving truck, and you have set up a nice smooth ramp where you are pushing a box up the ramp. Let's assume the box has a mass of 20 kilograms. The ramp is not that steep so that it is manageable for you. It's only 15 degrees. And the height of the ramp is 2 meters. To keep things moving smoothly, perhaps you want to know how hard to push. You're going to always push it horizontally. To get the box to the top of the ramp in under a minute. Or in less than or equal to 60 seconds. So we could start by first analyzing the forces that are acting on the box as it is being pushed up the ramp. So again, my system is the box itself, in which case I identify that the box is in contact with the ramp, so I'll call it FR, is in contact with you, I will call it FP, F person, and that's it. And then there's the long-range force of gravity. A free body diagram would look something like, there is gravity pointing down. There is the force from you pointing to the right. And then there is the contact force from the ramp almost pointing vertically upward. But since there's that slight 15-degree tilt, it is not pointing vertically upward, but is slightly tilted a little bit. Excuse me. Now again, you could look at this in terms of the horizontal and vertical components, or since we're worried about moving things up the ramp, we could instead look at this using a coordinate system that is parallel and perpendicular to the ramp. So if this is the ramp, drawn much too steep, the coordinate system I might use might be something that is parallel to the ramp and then perpendicular to the ramp. And that will be my coordinate system. And I will call this beta and alpha again. And this time I will have alpha represent going up the ramp, and beta will again represent moving off the surface of the ramp. I just slapped myself in the face. So now we have to, the goal next is to move our coordinates, or move all our forces into this coordinate system. The nice thing is that with this choice, the ramp itself points only along the beta direction. But now we also have the force of the person, and we also have the force from gravity. And all we know is that the ramp has some angle theta. Now in this case, we could again look for triangles and geometrically argue which angles are what. We've already done this with gravity, so I will just skip to the answer where that angle there is theta. And then I'll let you convince yourself that this angle is also theta. Sometimes the way I argue this, rather than doing it as a geometric proof, is I could imagine what were to happen if the ramp's angle were to decrease to 0. In that case, it makes sense that my coordinate system would rotate so that it was, again, horizontally and vertical. In which case, the force from the person better be pointing purely horizontal, and the gravity better be pointing purely vertical. And that is the case if theta goes to 0 and the coordinate axis rotates to 0. All right. So let me redraw. So the force from the person, what we just drew here is that there's the alpha direction and the beta direction. And what we're looking for with this angle is we're looking for this component, and then we're looking for this component. Or, I guess, this component. Just so then it is obvious where the triangle is. The triangle is right here, with this as a 90 degree. So then that's not too bad. The force from the person has a component along the ramp, which looks like it is then whatever the force is that it's pushing, I'll just call it F. That's what we don't know. That's actually what we're solving for. And then it looks like this is going to be cosine theta. And I'll put a plus sign in front of it or just leave it as is because it's pointing in the positive direction. And then as for the direction that I'm calling beta, I claim this is then minus F sine of theta. The sine of theta hopefully is clear from SOHCAHTOA. The negative sign, because it is pointing in the negative beta direction, it's pointing more into the ramp. It's not pointing off the ramp. All right, then there's gravity in this coordinate system. So drawing arrows here. Where I know this is the angle now. And so again, we're interested in this component and this component. So again, the triangle is here. Where we know this is a 90 degree, we know the other angle is theta, we're off and running. So then the force due to gravity, I claim the way it's drawn is going to be minus mg sine theta and minus mg cosine theta. And just to remember, this is the alpha direction, this is the beta direction. This is the alpha direction, this is the beta direction. For gravity, both with a minus sign, because it's pointing in the negative beta and the negative alpha direction. And then I guess we still have the, ramp, which is not pointing in alpha, but is pointing in the positive beta direction. So I'll write that as plus n. All right, so again, sum of the forces equals the mass times the acceleration. That is the force from the push plus the force from gravity plus the force from the ramp equals the mass of the box times the acceleration of the box. I could look at this in both directions, but really all I care about is the alpha direction. So I'm just going to look only in the alpha direction. In which case then I look at, I'm ready to introduce pluses and minuses. So I look at just the first components of all my vectors. So I got a 0. Looks like I got a plus f cosine theta. And I got a minus mg sine theta. Equals the mass of the box times the acceleration of the box up the ramp. Or I could say that the acceleration up the ramp is this f divided by m cosine theta minus g sine theta. If only we knew everything. You know, I know theta, I know g, I know m, but I do not know f. That's ultimately what we're going to solve for. So you could think, has this all been for nothing? It has not, because now we can connect it to other things we've learned about in this course. The assumption is that you're pushing with a constant force. So F is a constant, M is a constant, theta is a constant, G is a constant, sine is a constant. All of this is a constant. So this is all a constant acceleration. If it's a constant acceleration, what applies? The kinematic equations. So I could also say along the ramp, the kinematic equations apply. I could say, you know, the final position on the ramp is equal to the initial position on the ramp times the velocity along the ramp times t plus 1/2 the acceleration along the ramp t squared. Where here I know t is 60 seconds. You know, the idea is that I can do this in less than 60 seconds. So 60 seconds is the longest I'm allowed. And which of these do we know? We know the final height. Now I have to be careful, because I just said height and that was incorrect. This is the distance along the ramp. So what I'm asking for here, the initial position along the ramp, we can set that equal to 0. There was no initial velocity, we can set that equal to 0. And this we just solved for. And t we know. But what is the total distance the box has to go along the ramp? Not 2 meters. It is going the entire length of the hypotenuse. It is covering this distance. That is the distance you have to push the box. So then you could ask, do we know what this is? You know, I might call this R final, or the length of the hypotenuse. Actually, I'll just call it L. Well, we can't use tangent, we can't use Pythagorean's theorem, but we can say that sine of theta is opposite over hypotenuse. or that the hypotenuse is 2 divided by sine theta, 2 meters technically. Which, if you plug in theta of 15 degrees, this ends up being 7.73 meters. That's how far you have to push the box to get up the ramp. And you can now plug this in for that. And in this case, we know everything except the f in the expression for the acceleration. So you can algebraically solve for that f at this point. And I will just give you the answer and let you convince yourself by solving yourself. If you do this, you should get that the force you have to push is about 5¼ newtons. If you do that, the box will accelerate up the ramp such that you will get to the top of the ramp after 60 seconds. I leave it to you as an exercise. I'll put the answer in the margin, but this is a try me. Suppose you get to the top of the ramp in 60 seconds. You step out of the way and stop touching the box, thinking the box was secured, but the box then starts from rest and starts to accelerate down the ramp from just gravity. How long does it take for the box to get all the way back to the bottom? So you should get it is about 2.47 seconds. Gets all the way back to the bottom much faster than it took you to push all the way to the top. You might ask why. This is a physics class, we could ask why. Because you had to push it with a certain amount of force that not only accelerated the box up, but also beat out gravity. Because gravity was constantly trying to pull the box down. So you had to not only beat out gravity, but then whatever was left over you could use to push the box up. All right. That took much longer than I thought it would. Friction. Friction is the reason why you have so many misconceptions about how the world works. Why Newton's first law likely is very confusing to you. Where Newton's law again is saying that an object in motion will stay in motion for the rest of eternity, unless a force acts on it. Where you are likely more used to the fact that if something is moving, after a while it seems to slow down and come to rest. It seems, in that case, if we don't know what to call what's going on, or understand what's going on, we might say that the natural state of the universe is at rest. Where that is flawed is that it is ignoring the fact that there's this thing we call friction. There is an opposition to motion. This is a force that wants to ultimately do nothing else but bring the velocity to zero. So it has no other desire but to make the velocity vanish. This is very common with your everyday experiences. Push something across a rough surface, it moves for a bit and then comes to rest. Why? Friction. Why are balls and wheels so useful? The entire point of a wheel is to eliminate friction. Imagine a cart being pulled by an ox, but there are no wheels on the cart. That ox is not happy. It has to do a lot more, it has to exert a lot more effort in order to get the box moving down the dirt road. Put on some wheels effectively all they're doing is getting rid of the friction force that is trying to bring the cart to a stop. The ox now has a much easier time making the cart move. The point of a wheel is to eliminate friction. But not all friction is bad. Friction is the reason why when you make a sharp turn, that your car actually turns rather than just careens off of, say, a cliff if it were to move in a straight line. We talked about circular motion. You can imagine a car rounding a bend. It's rounding a bend, so there must be some force acting on the car to make it turn. Its velocity vector is rotating. That means there's an acceleration. By Newton's laws, that means there's a force. What is that force? When you take a circular turn, what the force that is providing you the ability to actually turn is friction. Friction between the wheels and the road. Which, again, is why I alluded to that slippery roads, right? Too much centripetal acceleration is bad because that can effectively beat out friction, which is what is keeping your car moving in a circle. All right. So what is friction? If I were to model friction, how might I do that? We've been kind of drawing things as very smooth surfaces and objects. A box, I drew it as a perfect box moving across a perfectly smooth floor. But I could put a magnifying glass up to what's going on here. And if I were to zoom in and see what's going on, I would see that the box and the floor are not perfectly, not perfectly smooth. I should have used different colors. Let's make the box red. So then if I zoom in, this is the box. And this is the floor. I could zoom in even more and look even closer to what's going on. And I would find that there is actually a lot of imperfections in what makes up the surface of the box and what makes up the floor itself. And you can imagine if I look at those zigzaggy lines and I were trying to make one move across the other, there would be some resistance. Some of those grooves would get hooked or stuck on grooves of the floor and of the box. And they might work against each other to try, as the box moves, it might get caught. Which, as a result, there would be, if I were to do little free body diagrams, there'd be tiny little forces that are pushing on these grooves and these hooks that might act to ultimately slow down the box if the box is moving. You could ask even what's going on even more. You could zoom in even more and ask what is going on at the most fundamental deep down molecular level. And friction is nothing other than, we would say friction is actually an electromagnetic force. That what's going on, if you really were to zoom in at the point of contact between the box and the ground, really what's happening is things are close enough that the molecules that make up the box and the molecules that make up the floor are electromagnetically interacting with one another. They might be sharing electrons. They might actually be, the bonds that make up the box and the floor might actually be changing as a result of the presence of the other ones. There might be tugs and pulls electromagnetically as a result. At points, the box can even fuse to the ground and vice versa, where there's little points where the box and the ground become one, and they try to form a bond with each other, which then immediately gets broken as soon as the box keeps moving, for example. So at the fundamental level, friction is an electromagnetic force that is really the interaction between the molecules and whatnot that make up one object that is rubbing against the other object. We will, in this class, model friction using a much simpler formula. We will, and this has been verified by experiment, that for in most cases, friction between two surfaces in contact with one another can be modeled very simply based on how much they are in contact with one another, which will connect to what you might want to call the normal force, what I will want to call the contact force between the two. That is a measure of how really they are in contact with one another. Are they pushing really hard against one another, or are they just barely resting on one another? And an experimental measure of how strong friction is, which are called the coefficients of static and kinetic friction. Take the case of a box on a ramp. I have this here. This box and this leather tote is not smooth. There is definitely friction going on here. If I have things perfectly vertical rather, then I could ask, there is no desire for the bag to move to the left or to the right. Gravity is pointing downward. The contact force, the surface force, is pointing perfectly upward. They're in balance. There is no acceleration in the horizontal direction along the box. Now I could increase, let me do it so you're seeing edge on. I could increase the angle of the box ever so slightly. Now what's going on? Notice the bag is still not moving, so something has to be in balance still. If I look at my photo, gravity is still pulling downward. Now the contact force is kind of at an angle. And if that were it, there would be a net acceleration down the ramp. Part of that normal vector that I drew, the contact force, part of it points along the ramp, down the ramp, and part of it points perpendicular. I'm sorry, that is completely wrong. Ignore everything I just said. Gravity has a component that points along the ramp and perpendicular to the ramp. The contact force always points perpendicular to the ramp. Ugh. Gravity, however, now has a component that points, part of it points down the ramp, and then part of it points perpendicular to the ramp. So there's this component of gravity that wants to pull the box down the ramp. And if there were no other forces in town, then that's exactly what would happen. So there's some, I think I called it alpha, to correspond to along the ramp. But we saw when I did this, the object was not moving. Therefore, the sum of the forces must equal 0. There must be some other force here that is pushing back, which I will call F sub S, for static friction. Things are remaining static. The velocity vector is 0. That is what friction wants. So friction is happy and content and will do what it can to make sure that remains the case. Things that are static remain static. Static friction. And I could actually calculate with the drawing I just drew. I could actually, if I knew theta, for example, and I knew the mass of the box, I could actually calculate how much static friction is, what the static friction force is for this example. And let's say it was this. Now suppose I increase the angle a little bit. So maybe not, increase it too much. So initially I had something that was at this angle. Then say I increase it to this angle. I keep increasing it by too much. Let me start with a shallower angle. So here's my initial angle. And then I increase it a little bit more. In this case, the bag still is not moving, even though I increased theta. So if you go back to this drawing and I make now theta a little bit bigger, I'll just redraw it. If I make theta bigger, maybe I'll call it phi instead, and the box still is not moving, notice there's still a gravity component that points down the ramp. We calculated that before. It was mg sine theta. Now in this case, sine phi. Theta has gotten bigger, so mg sine theta has gotten bigger. But yet, the box, or in this case the bag, is still not moving. So there must still be a friction force, a static friction force, but it is bigger in this case than it was previously. If I call this static friction 1 and static friction 2, this must be bigger than the static friction in the first case. Okay, so the static friction force has a variable amount of force that it can exert. You know, if it's just a tiny little tilt, there's a little bit of static friction to make sure everything is in balance. There's a little bit more, there's even more static friction, even more static friction. But eventually there reaches a point where the object starts to move. Static friction loses out, and eventually the box, or the bag in this case, starts to slide. So F static can be any value between 0 and some maximum value. I'll call it Fs max, say. After that point, F static fails, and the object begins to move or slide. So static friction, the velocity vector is 0. It wants to keep the velocity vector 0 as long as possible, as much as it can, even though the static friction, or actually gravity, is getting better and better and better, but eventually static friction will give up and not be able to do enough, and the bag will start to accelerate downward. Once it starts accelerating downward, notice in this case, it is accelerating downward at a rate that is pretty slow compared to if there was no ramp and an object that just falls with gravity. So there's still friction. If you've ever slid down a hill, sledding is fun because your sled in the snow make friction very low. If you tried to go sledding on just a dirt hill, you don't get very far because there's still friction that pulls your sled to a halt. So we'll say once you start sliding, there is still friction. But it is kinetic friction. And I might call that a symbol FK instead. So to summarize, let me summarize, and then I think I will just call that it for today's lecture. And then we can go into this more in the next lecture. So F static requires that V is 0, and it wants to keep V as 0. It wants everything to stay stationary. Can be anything up to some maximum value. Once, so if it's mg cosine theta, say, or mg sine theta rather, it's mg sine theta pulling the box down, F static pulling the box up. Eventually, mg sine theta is too big, such that it's bigger than this maximum static friction. Static friction therefore gives up. Then that becomes F kinetic, which only operates if there's motion. There has to be motion for kinetic friction. It points in the opposite direction as v and is a constant. In the sense that it's not variable like the static friction force can be. Here's kind of an example of something you might do in a lab where you're measuring, say, the force being exerted by friction as perhaps, say, you increase slowly the angle of the ramp, for example. So it says time, but we can think of this. I think we can think of the analogy as you're increasing the ramp angle. As you increase the ramp angle more and more and more, there is more static friction that is needed to prevent the box from moving, say. Eventually it reaches some maximum amount and it gives up. The box starts to move, in which case the friction force does not go to zero, but it drops to some roughly constant value as it begins to slide down the rough surface. So this constant, when there's motion friction, is kinetic friction. This static friction, when the object is not moving, is something that can have a range of values up to some maximum, but requires that the object itself is not moving. So this F static max, we model as some number times the normal component, or the normal force that is acting on the object that is experiencing friction. So this is just a number called the coefficient of static friction. And then this is the contact force from the surface. So static friction can be anything up to whatever this number is. So coefficients you look up in a book, you calculate via Newton's laws the normal force. That tells you how much static friction can do. If static friction fails, then it becomes kinetic friction, which is the same formula, but a different coefficient. So we say this is the coefficient of kinetic friction. So the kinetic component is, kind of by definition, always less than the static component. Which is why, of course, then the force drops when things start to move. All right, so we will recap this, and I'll do an example or two using friction as the beginning of the next lecture, which will also include Newton's third law of motion.